All right, before we get into any of the really good course stuff, what we're going to start off with is just a few prerequisite skills that hopefully you remember some of from grade 11 or 10 or 9 or whenever you first learned them. I do realize that it's hard when you've been away for a while, so we're going to take a look at just a few of the things that we're going to be using semi-regularly in the course. I've listed a few of the skills specifically at the top under terminology, but we'll kind of just go with it and see what we find along the way as we go work our way through the questions. First thing I want to take a quick look at is function notation, something that hopefully you do remember. It's pretty straightforward. It's basically the idea of a function, which we can call anything we want, but usually we'll use f. And the part of the bracket does not mean f times x, just a big reminder. This just means that the function f is a function of x. And you can have anything you want. So for instance, you could talk about things like the height of a ball at time. That would mean that height is a function of time, or so on. Lots of these appear in physics and the physical sciences, as well as lots of mathematics stuff. But yeah, they're pretty common. So remember that a notation, like for instance, f at 0, basically just says wherever you see the variable or the thing in the bracket, replace it with a 0. So here we see we have f at x equals x squared minus 3x. And x is really just a placeholder saying where to put in that value. So f at 0 is just going to be 0 squared minus 3 times 0. And I think we're probably at that point in our mathematics careers where we could do this in one step mentally. 0 squared minus 3 times 0 is 0 minus 0, which is 0. If you feel a real need to put an extra step there, please be my guest, but I think for the most part we don't need to do that. Similarly, f at 4 is just going to be 4 squared minus 3 times 4. Now this one I'll do one extra step just because I feel like it. 16 minus 12, so f at 4 is equal to 4. F at negative 5, it'll just be negative 5 squared minus 3 times negative 5. And hopefully this is all coming back to you. It's pretty straightforward. Don't forget the double negative there. Negative times a negative becomes positive 15, so that's 40. Now this is really what often trips students up, and I think it's kind of interesting because I don't think it's particularly a difficult idea. We saw that when we have, again up here, f at x equaling x squared minus 3x, well, what do we have when we want f at r? And a lot of people are like, oh, I don't know what r is. The correct answer is it doesn't matter what it is. It says wherever you see an x, plug in an x. Wherever you see an r, plug in an r. So that'll just be r squared minus 3 times r. Can we evaluate that or do anything with it? No, not really. But that's what happens when you plug in x equal to r. Now these ones in grade 11, my students are always baffled by these ones. But this is still saying the same thing. It's saying wherever you see an x, replace it with x cubed because we have a function f at x. So f at x cubed is just going to say x cubed squared minus 3 times x cubed. Again, it's a placeholder. The x is a placeholder. The fact that this is another x doesn't make any difference. It just says wherever you see that thing, replace it wherever it shows up in the f at x formula. And by the way, we're always referring back to this. We can't say what f at x cubed is unless we know what f at x is. Okay, so now we get to take in some advantage of our exponent laws, if you remember those. Exponent of an exponent, multiply them, that's 6 minus 3x squared. And that cannot be simplified. Oops, sorry, that should be a cube. My apologies. I guess technically I do have a eraser here on my pen. One sec. I can actually properly erase. Ooh, fancy. And then write it in proper. X to the 6 minus 3x cubed. Okay, and similarly, f at x equals x squared minus 3x means that wherever we see the thing, we're doing x squared minus 3 times that thing. In this case, the thing we're plugging in is 2 minus x. This one here, again, yeah, I think we can expand that manually. 2 minus x times 2 minus x is 4 minus 2x minus 2x plus x squared. If you need to write an extra line for that, again, be my guest. And then we do the minus 3 times 2 is negative 6, and minus 3 times minus x is plus 6. Sorry, plus x. Plus x, not plus 6. By the way, I'm doing one take on this. I don't have time to edit everything. It's way too time consuming. Okay, now what we're going to want to do is what I want to do is take advantage of the fact that I have multiple colors here and collect like terms. So I have an x squared. Where did my thing go? Come back, come back. But don't save image, bring it back. Sorry guys. Jeez, all over the place. Okay, I'm going to pause for a second till I can figure this out. Okay, I think I got it. Okay, so that gives us x squared. And then we have a minus 2x minus 2 more x's plus an x. That's plus 3x. Sorry, minus 3x. And then we have a 4 minus 6 is negative 2. Okay, and that's it for that. That's how those are done. I think I found out how to... Yeah, I still have to play with this a whole lot. Anyway, I figured how to get rid of this border at the side and the top and all that stuff. But until then, here's how we do it. Okay, state the slope and y-intercept for each line. Well, this is actually pretty easy. This part right here, the number in front of the... This is a trick question. I was going to say the number in front of the x gives us the slope, but there's multiple x's. So we're going to have to simplify this a little bit. I'm guessing this was a typo. And I say I'm guessing because I typed it up a while back and I don't remember. Negative 3x plus x is negative 2x. And now I'll say the number in front of the x is the slope. And usually we denote that with the letter m. So slope equals negative 2. And I can think of this as plus 0. Normally that number at the end, whether it's positive or negative, is the y-intercept. And we usually denote it as b equals. So in this case, the b-intercept, some people say it doesn't exist. It does. It's just equal to 0. It's a little bit hidden there. Okay, in this second one, we got to make sure I got to make sure I don't make the same mistake again. And so I'm going to expand this and move it around so that it's in the proper form to determine everything. So I'm going to start off by, first of all, expanding over here. So that'll give me negative 3x minus 2. So that's dealt with this part. That negative 4 comes over here, becomes positive 4. And that simplifies to negative 3x plus 2. All right, same idea before. The part in front of the x, the coefficient to x, is the slope. M equals negative 3. And the part at the end is the y-intercept, which we call b, and it's equal to positive 2. Not too tricky. Moving right along. Determine the equation for the linear function that satisfies each set of conditions. So we have down that the slope is 4. Since I was using red for that 4, I'll do it again. And it goes through, technically that's not a y-intercept, that's just a point. It goes through 2, 5. Here's what I'm going to remind you of, and that's that all linear functions can be written in the form of y equals mx plus b. The good news is we got the m. So I can say y equals 4x plus b. We're almost there. We're halfway done. At least halfway in the sense that we've gotten one of two variables. Now we have to make sure that it goes through this point here. Oops. 2, 5. Reminder that the 2 is the x, the 5 is the y. So I'm just going to plug that point into my equation and say 5 equals 4 times 2 plus b. 5 equals 8 plus b. Subtracting 8 from both sides gives me b equals negative 3. By the way, I like writing the variable on the left-hand side. It doesn't really matter. We could have stopped right there. We had our answer. I'm always surprised when I ask students a question like this on a test. They all get that far, and they've done 99% of the work, but they haven't actually answered the question. The actual question is, what is the equation of the line? And that equation would be y equals 4x minus 3. By the way, for the most part, for non-detailed word problems, I always believe in putting a therefore statement in questions that involve, Johnny went to the store and bought something, blah, 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 what did he, whatever. For questions like this, where it's state the equation or determine the equation, I like putting just a box around my answer. I guess I put a box around too many things here. But hey, that's why I have an eraser. Here we go. I put a box around my answer just to kind of draw your eye to it. That's usually how I'll do it. Now we've got a similar question. We have a line that goes through 2 points. Well, this would be easy if we had a slope and an intercept. We have neither of those things. The good news is, if you recall, slope, m, equals rise over run. And there's different ways of writing this. You don't by any means have to do all of these. I'm just going to kind of show you different ways. I know teachers do it. They might say it's equal to delta y over delta x. Delta is a fancy term for change of, which is equal to y2 minus y1 over x2 minus x1. Now, it doesn't really matter which point is which. It's irrelevant, but I'm just going to say that this is x1, y1, and this is x2, y2. And then when I plug stuff in, I get 1 minus 7 over 5 minus 3 equals negative 6 over 2, which is negative 3. So that gives me my slope. Once I have that, I go back to do exactly what I did last time. Y equals mx plus b. Plug in my fancy new slope of negative 3. Pick a point, any point. It doesn't matter which one you do. I am going to choose 5, 1 because the numbers are a little bit smaller, and I think it will be a little bit prettier, but it'll work out either way. So I plug in y equals 1, x equals 5, and I get 1 equals negative 15 plus b, or b equals 16. Solving it and reversing the sides at the same time. And now again, to make sure I've actually answered the question, I'm looking for an equation, which is y equals negative 3x plus 16. I think just for a moment, I'm going to switch over to Desmos, a graphing program, and take a look and just make sure that that actually does work. Okay, so I've opened up Desmos. I've already put in those 2 points that are on our line, or are supposed to be on our line. That's 3, 7, and 5, 1. You can see that they've shown up here in red. I can actually zoom in a little wee bit. Not too much. And now I want to see if my equation works. So if it works, it should go through those 2 points. And I have y equals negative 3x plus 16. And it certainly does look like it goes through those 2 points. So I think we're in good shape. Okay, kind of cool, huh? By the way, I'll be completely honest. I love Desmos like it's my own child. I find it the greatest program ever written. At least the greatest online graphing calculator ever written, which is kind of not the same thing as the best software ever. But anyway, moving right along. By the way, I think you may have noticed that I leave a lot of space for some of these questions, more than I possibly could need, and it's just in case I want to write down anything, extra or interesting, not necessarily because I think I'm going to need that much space. I hate running out of space, so a little extra never hurts. And this is all digital anyway, so who cares? Okay, question 4. Determine the equation for a quadratic function that satisfies each set of conditions. And this is where I will take advantage of the fact that I do have a little extra space over to the side. And I want to remind you that there are several different ways of writing a quadratic function. So I could write it as ax squared plus bx plus c. That's one way of writing it. I could write it in vertex form. This, by the way, is general form. I don't know why it's exclamation, but anyway, it's very excited general form. I could write it in the form of vertex form, which is ax minus h squared plus k vertex. I could write it in factored form, which is a x minus, I forget what variables we usually use for these, but I haven't used d or e yet. Something like that. Okay, depending on the version we have, sometimes it's easier to choose one thing versus another. For this particular one, I think I'm going to try and use this form right here, which is factored. Should have written that. And the reason for that is I have two intercepts, x-intercepts, -4 and 2, and there's a little bit of a trick I can play. I can start off with that equation, y equals a x minus d x minus e. By the way, d and e are completely irrelevant, like random letters that I chose. You can use whichever letters you like. And I can say now there's x-intercepts at -4 and 2. That's actually going to be my values for d and e. So this becomes x plus 4, x minus 2. And then from there, I could do a trick very similar to what we did with the linear. I can figure out what the a is by plugging in, the x-intercept. One second, my brain is freezing. Oh, yeah. I was going to say the y-intercept is 4, but I need an actual coordinate to go with that. Well, obviously, if the y-intercept is 4, that happens at x equals 0. So I plug in 4 equals a 0 plus 4, 0 minus 2. 4 equals -8a, and then divide both sides by -8. And 4 over -8 is -1/2. And from there, I can quickly get that the function itself is y equals... by the way, I said function. I'm putting down y instead of f at x. It doesn't really matter at this point. They're both perfectly valid. Y equals -1/2 x plus 4 x minus 2. Okay, so that's a perfectly good answer if I don't care what form I'm in. If I want it to be in one of the other forms, if I want it to be in general form, it's easy, just expand it and express it as ax squared plus bx plus c. If I wanted to get it into vertex form, I'd have to expand it, and then I have to do that whole complete the squares thing, which I don't want to get into right now because I think we're going to cover it later anyway. But I could do that. Now I do want to point out that yeah, you know what? Actually, I lied. I don't want to point it out. I'm going to leave the vertex form, all that stuff off here. No, you know what? Let's do it real quick. Okay, if I wanted to do it in this form, I could have done it that way. Y equals a x minus h squared plus k. And what I could do is take advantage of the fact that I know that quadratic functions are symmetric. So if the x-intercepts are -4 and 2, the midpoint of that must be -1. And that means that I know that this becomes y equals a, and hk is my vertex. So my vertex has a point at x plus 1 squared plus k. Now I remembered why I wanted to do this version right there instead of the vertex form. At this point, I can solve it. The problem here is that I have a lot of variables, y, a, x, and k. And I have 2 points that I know are on this. I can't use the point, I guess I could use that point, but I could use the points x equals negative 4, 0, and the point x equals 2, 0, and plug them into this equation. And that's going to give me 2 equations with 2 unknowns, and then I have to solve a system. And I could do that, and ultimately it's going to give me this answer, but it's going to take a while, and honestly, we've already solved it, so I'm not going to worry about it. I do want to show you that stuff like that. There's usually multiple ways to do it. So if you don't get the easy way, you might get the slightly harder way, but that might still be perfectly valid. And sometimes it's not even a matter of easy or hard. It's a matter of what you see first. If I had started this way, I probably could have continued it and finished it off relatively easily without going through all the work that we did to get to this one. But this one, so much prettier. I have to keep reminding myself as I'm making these that I can't just point to the screen with my pen where I want you to see. You have to actually I have to underline stuff so that you see it. Okay, the next one, we still want to find a quadratic function that has a x-intercept of negative 2 and a y-intercept of 12. Okay, there's a couple things going on there. The fact, and I kind of know this right off the bat, the fact that it only has one x-intercept, there's only one type of function, or quadratic, that only has one intercept. And that basically means that the graph is either coming down and just touching and going back up, or it's possibly, oh, that's not what I wanted. I want my thing back. Where's my drawing tools? There you are. Or I can have one that starts at the bottom and goes like that. But it's one or the other. It's just touching the axis and then leaving again. Okay. Much like we did last time where we got to choose which form we wanted, this time I think I'm going to use vertex form. And the reason for that is the single x intercept kind of gives us a vertex. So I'm going to start off with y equals ax minus h squared plus k. And I'm going to plug in my x-intercept. My x-intercept basically is the vertex. Y equals ax minus negative 2 is plus 2. And now I'll do what I was mentioning in the last question. I've got 2 points that I can plug in here. I have x-intercept of negative 2 and a y-intercept. Y-intercepts happen at x equals 0 of 12. So if I plug in those 2 points, I'm going to get 2 equations. 0 equals a negative 2 plus 2 squared plus k. Well, actually, that's going to make my life really easy, since that becomes a times 0 squared, which means that k is 0. Wait a second. I know from vertex form that k would have to be 0 because it's not above or below. Remember, if k is positive, it's above the axis, and if k is negative, it's below the axis. Oh, I could have taken such a shortcut there. I do want to point out I've been doing math for 20 years, and I don't always see the most obvious thing first. Sometimes I have to find it too, so we all have that issue. Either way, once I've plugged in k equals 0, I then have y equals ax plus 2 squared. And now I can plug in my other point, 0, 12. By the way, if you plug in this point again right there, what you're going to get is 0 equals 0, which doesn't tell you any information. If I plug in this point here, not my eraser, my pen, I meant to make that in green. Then what I can do is get y is 12 when x is 0. 12 equals 4a. A equals 12 over 4, which is 3. And now that I have that information, I can state my equation is y equals 3, x plus 2 squared. I was going to say there is no k value. That's not true. There's a k value of 0, but it doesn't show up in our formula. So there's our function, and we're done. With any of these, you can play around with them. There's a whole bunch of ways you can get to the right answer. I'm just showing you one, or in this case, I attempted to show you two and just gave up on one of them because it was going to take too much room. But we kind of did the same idea here. Okay. Okay, I'm just going to point out that I actually have already done question 5 over the last 5 minutes, but I botched a sign in it, so I had to erase it, and now I'm retaping it. The only reason I'm bringing that out to you is to point out that if this was a real class, chances are somebody would have put up their hand and said, "Hey, Mr. Ray, you have a sign error there. That should be a negative." And I wouldn't have wasted that 5 minutes. So even though this may seem like it's faster in many ways, it's so much slower for me. It's painful. But anyway, let's get back to doing question 5. Okay, we need to find the x-intercept, vertex, and direction of opening for each quadratic function. Starting with the first one, the x-intercepts are actually a little bit tricky to find on here. The vertex is actually fairly easy. I'm going to just write that here. The vertex is going to be the opposite of that, because that's the x-intercept. Or sorry, that's the x value of the negative of the x value of the intercept. You know what I mean. It's the vertex point. And this is the y value of the vertex. So there's our vertex. Our direction of opening, because there's a negative sign in front, is going to be down. So direction of opening is down. And now the x-intercepts are a little bit tricky. X-intercepts you always find by setting y equal to 0. So 0 equals negative x plus 5 squared minus 2 is negative x squared plus 10x plus 25 minus 2 equals negative x squared minus 10x minus 25 minus 2 equals, technically I mean that's good enough, but I hate having negative coefficients in front of x squared, so I'm going to multiply both sides by negative 1. Negative 1 times 0 is still 0, and this becomes x squared plus 10x, and minus 7 becomes plus 27. So at this point, I could try to factor that if I can think of two numbers that add to 10 and multiply to 27, and there are very few things that multiply to 27. 3 times 9 and 1 times 27. Neither of those is going to work. So now I have to pull out my quadratic formula, and my quadratic formula unfortunately is very long, and I don't want to waste your room here, and honestly you know how to use quadratic formula. So what I'm going to do is pause, solve it, and come back and write down the answer. And using my magic of pause, I figured out that there are no x-intercepts. And that's actually fairly easy to justify, because if you think of the quadratic formula, you've got the part in here with the negative b squared minus 4ac. And that's going to give us 10 squared, which is 100, minus 4 times 1 times 27, which is more than 100. So that ends up being a negative value, and you can't take the root of a negative number. So no x-intercepts. All right, moving along to, actually, you know what, before we do that, let's just take 1 second and pop over to Desmos and see if it actually gives us what we think it will give us. And hopefully it will. Okay, so there it is. I punched it into Desmos, and when I look at that, it does have a vertex at -5, -2, so we nailed that. It definitely opens down, and it also definitely has no x-intercepts because it's not touching the axis. So we know we've done something correct. Going back to part B of our problem, we need to find x-intercepts, vertex, direction of opening for that. Good news is x-intercepts are actually really easy to find when it's in factored form like that. It's just going to be the negative values of those, since this is in the form of x minus d, x minus c, etc. So x-intercepts are 2 and negative 4. The vertex, vertex could be a little bit tricky in this case, but I think we can figure it out. There is a little trick to this one. And when you see that I mean, there's several ways to do it. I think the fastest way to do it, though, is to acknowledge that the midpoint of the two x-intercepts is x equal negative 1. So we know that the vertex is going to have an x value of negative 1. We just need to know its y value. But the good news is we can just literally plug it in to the original equation. The value for y when x is negative 1 is just 3 negative 1 minus 2 negative 1 plus 4, which is 3 times minus 3 times plus 3, which is negative 27. So that should be the y value of our vertex. We'll go to Desmos to make sure it's correct after. And direction of opening. Coefficient on this thing is positive, so it's just going to be up. Okay, so let's pop over and see what that actually looks like. Okay, so I've punched it into Desmos. There's what it looks like. Direction of opening's up. That's good. Vertex is way down here at negative 1, negative 27. Nailed that one. And its x-intercepts are certainly negative 4 and positive 2. So I think we're doing good here. All right, let's keep moving along. Seems like it's getting really long, or at least it feels like it's getting really long. Okay, finally some fast ones. Actually, the last two questions are pretty quick. So we want to use finite differences to determine if each table of values represents a linear or quadratic function. For those who don't remember what first differences are, they're basically just going here and saying what happens as we change from 1 to 1. Now, first thing we should do is make sure that the x values go up by the same amount each time, and they're going up by 1, and the y value is going down by 3. So it's basically 7 minus 10. The next one is 4 minus 7. 1 minus 4, negative 2 minus 1, negative 5 minus negative 2 is negative 5 plus 2. Hey, they're all negative 3. The fact that the first differences are all the same is going to lead to the conclusion that it is linear. The next one, again, checking my x values are increasing by a similar amount each time. Negative 3 minus 3 is negative 6. Negative 5 minus negative 3 is negative 5 plus 3 is negative 2. Negative 3 minus negative 5 is negative 3 plus 5 is positive 2. 3 minus negative 3 is 6. 13 minus 3 is 10. Okay, those are definitely not the same. However, going from negative 6 to negative 2 is an increase of 4. Going from negative 2 to 2 is an increase of 4. 2 to 6 is an increase of 4. And 6 to 10 is an increase of 4. These are the second differences. And because they are the same, we can conclude this is a quadratic. And the final one, again, making sure the x values are all going up by the same amount, which they are, by 1 each time. This is going up 4, up 2, down 2, down 4, down 6. Second differences. Oops. Down 2. 2 to negative 2 goes down 4. Negative 2 to negative 4 is down 2. Negative 4 to negative 6 is down 2. So they almost all go down 2, except for this one screwed it up. And that means that this is neither. Maybe something else, but it's not that. Okay. And the final question, state the domain and range of each function. All right, that first one there has something, I don't know if you recall the name for it, but that is a asymptote. Hopefully it's a word that rings a bell. And I realize that that's extremely small to see, so I'm just going to zoom in because I have that magical power. And that definitely looks like it's at x equals 3. So there are different ways of writing domain and range. And I just want you to remember that domain, whoa, my palm definitely moved that. Domain is all x values, range is all y values. I always remember the domain because, you know, the old kings and queens of days past, when they all went out and inspected their domains. Domains are pretty horizontal. Most of the kings didn't look up in the sky to see what they owned. So anyway, that's how I remember it, but you can remember domain is x, range is y, whatever works for you. Okay, so it looks like for x values, I'm actually just going to switch my color here to red so it looks kind of like the graph itself. There should be arrows on here. The graphing program I use obviously doesn't put them on, but it's going up there and down there. The x values seem to go up to infinity in this direction and down to negative infinity in that direction. They seem to be everything except 3. So the way that I want to write that, once I find out where my thing went again. There we are. Move it to the side. The way that I like to write this is set notation. There's a couple ways of doing it. We'll talk about both as we go on further into the course, but I'm going to say that the domain squiggly bracket, x is the element of real. And by the way, if you're not used to that way of writing it, that's okay. The second thing, this is set notation, which you actually talk about a fair bit in data management. But x is the domain, or sorry, x is the element of real, which just means that x is a real number. This part here just says is an element of, and this part here is a real number. For some reason, I'm not sure. Number sets usually get the double vertical bar at the beginning of them. So the R has 2 lines instead of 1. And anyway, you'll see it. It's kind of common. If you just want to write a regular R, that's fine. I'm not offended. But we'll say x is the element of real, and then I put a vertical line that means such that, and you may also see just a comma here as well. They're both accepted. X is the element of real such that x is not equal to 3. So there's a fancy way of saying x can be any number, any real number, except for 3. And that's it. Range, very similar, and I'm going to zoom in again. There is actually another asymptote there, a horizontal one. And that would be at y equals 2. So this is just going to be y is the element of real such that y is not equal to 2. And that's it. I'm going to show you in a moment another notation and explain also why it doesn't work so well all the time, why I prefer this notation. Over here, domain. Again, I'm going to zoom in just so you can see it here. And if this was a little bit more clear, I'd put a dot there to show that it actually exists at that point and that it goes on forever over there. My apologies, this thing bounced around a little easy. Okay, so I'm going to say again here, x is the element of real, such that, and it looks like x can be anything bigger than 3. And I'm just going to put this on here so I don't have to zoom in again. X is anything bigger than 3 or equal to. So x is the element of real such that x is greater than or equal to 3. And the range, y is the element of real such that y is greater than or equal to -4. Okay, so that's one way we can write it. There is another way that's actually shorter, and it just looks like this. Since x starts at 3 and goes to infinity, we say 3 comma infinity round bracket. Now the neat thing is the square bracket says that that first value is included. It's part of it. 3 is valid for x. This last part says that the value is not included. It goes up to that point but doesn't actually touch that point. And it makes sense because you can never reach infinity. So infinity always gets a round bracket. If this had been x is strictly bigger than 3, then we would have had a round bracket on there. But because it's greater than or equal to 3, we don't. And likewise, y goes from -4 up to positive infinity. So that's how we could write it. Now, this notation is the notation most students like because it's a lot shorter than this notation. But there are some problems with it. It doesn't distinguish between number sets, so maybe only natural numbers, counting numbers are included in this. Maybe it's just 3, 4, 5, 6, not real numbers. This one doesn't specify. Also, it becomes very difficult to use that notation when you've got exclusions like this. So it's hard to say where you start and stop when you start and stop more than once. So because of that, I prefer this notation. I realize it's a little bit longer, but I do like it better. But we will use both. Okay, this is going on way too long, so we're going to stop there. If there's some homework questions to try, just go give them a shot. You'll find them under the textbook stuff under lessons in the course. And I've given you a few hints here. If you are having problems, by all means, please access this file. It's got it's basically an appendix that tells you how to do a bunch of different things. And then there's a couple hints there on how to do question 8 and 9 to 12. Just usually I'll give you little hints down here if there's something to do or something you can skip over or something that makes it easier or whatever. So I'm going to stop there and let you try some questions on your own. I wish you the best of luck, and we will take up any questions that give you a hard time. Until next time, got to switch back to myself so you can see my face before we go. Have fun and enjoy math as best you can.